So let's jump into redox now. And we're really going to start off with the basics. So what you're going to find is we're really going to cover the basics of redox. The reality is, and I'm going to preface this, that I personally still think, despite the fact I've tutored chemistry now for 6 years, and I believe my knowledge is probably greater than what it was. It's definitely greater than what it was when I went through year 12. I still believe redox chemistry is probably the most difficult topic in 3-4 chemistry. I think the breadth of which they can ask questions is the most. There can be more difficult questions on the background of this. And I also believe that at times, redox chemistry is planted in the basics. And if you don't know your basics well, you'll really struggle to maintain your knowledge. So I'm a big believer that our redox chemistry really importantly needs to be strong. You need to know your redox chemistry really well, and you need to know your redox basics well to know your redox chemistry well. So, moving forward, redox and oxidation. Redox is made up of reduction and oxidation, and so we know that oxidation involves a loss of electrons, reduction involves a gain of electrons. It's good to know the acronym oil rig. Oxidation involves loss, reduction involves gain, and therefore you get your acronym of oil rig. It's good to know sort of your basic structure of half equations. So I use M as like molecule. Molecule goes to molecule ion plus electron, and that gives you sort of oxidation, whereas reduction is the opposite. You get your molecule ion plus your electron goes to your molecule. So oil rig is your acronym. In a redox reaction, one species is the oxidant and the other is the reductant. That's really important to understand. And the terminology is super important. Now, I don't want to harp on about this because I feel like sometimes the more you talk about this, the more you confuse yourself. But it's important to understand that the oxidant itself is reduced, but causes oxidation of the other species, much like how a teacher does the teaching. Again, the same thing. The reductant causes reduction, and therefore it itself is oxidized. You cannot have one without the other. That's super duper important. But the oxidant causes oxidation. The reductant causes reduction. So in the other way that you can sort of think about it is the teacher does the teaching, doesn't get taught themselves. They do the teaching, just like the oxidant does the oxidizing. So essentially, the oxidant causes something else to be oxidized, but it itself is reduced. And that's a really important sort of distinction you need to be able to make when going through this stuff. I'm just getting up a good pen color so we can sort of do some drawing as we go through. All right. Redox reactions, importantly, cannot happen without both. So you cannot have oxidation without reduction, and you cannot have reduction without oxidation. That is the reality of this situation. One must happen without the other. You cannot separate them. Electrons cannot be lost, nor can they be gained. They must be conserved. It's much like the idea of energy for those who do physics, and again, this is in chemistry as well. But the idea of energy is never lost. It is just transformed. We talk about this in chemistry. We talk about it more in physics, but it's an important idea. So same thing with electrons. Energy or electrons cannot be lost or randomly gained. They must be transferred. So then I say to you, all right, well, if I provide you with 3 different equations, and I've provided you with 3 different equations here, which of these is a redox equation? And unlike in a diagram that you sort of saw before with like the oil rig and the different equations, you can't explicitly tell you where is the electron movement, what is going on. You can't look at those half equations that I showed you before. So in this case here, we have to use oxidation numbers, or what sometimes the exam will refer to as oxidation states, to determine if the equation is redox or not. So there's a few rules to remember, and you need to feel comfortable with these. So the first rule here is the idea that oxidation states of free elements are always 0. So as you can see here, your oxidation states of Fe solid, your Na solid, your Cl2 gas, they're going to be 0. Your oxidation states of simple ions are always going to be whatever the ion is, the charge of the ion. So +1 for sodium, -1 for chlorine, magnesium's +2, etc. In compounds, there's a few different rules. So in compounds, it's really important to understand that the main group ions or the main group metals, and the ions of those metals are usually what takes precedence. So the metals are usually at the front. So if we look at something like sodium chloride, the sodium is the metal, therefore the sodium is going to keep the +1. So as you can see here, this is the +1 here. Now, if you have your magnesium, you're going to have your +2. Therefore, from there, you sort of work off everything else. So as you can see, sodium chloride here, it has an overall charge of neutral, 0. Therefore, the chlorine is going to be a -1. So you'd put a -1 above the chlorine. Now, on the other hand, you've got magnesium bromide. There's 2 bromides there. So therefore, they're actually going to be -1 each, but you're going to have 2 of them because they're overall going to cause a charge of 0 over here. And that's essentially how that's working there. Now, hydrogen is almost always +1. Oxygen is almost always -2. The only example I want you to know where one of those is not what it says there is oxygen in hydrogen peroxide. Hydrogen peroxide is H2O2. Hydrogen peroxide is, I don't know if you've seen maybe you've seen movies, especially like wartime movies. Hydrogen peroxide is what they used to use as sort of a poison. And hydrogen peroxide is essentially a very deadly poison. And I think we still use it in some cleaning products, and we still use it in some pesticide poisons, etc. But essentially, hydrogen peroxide is a very unstable molecule because the oxygen is -1. So you've got 2 hydrogens, which are +1 and +1, and then you've got an oxygen, or 2 oxygens actually, that are -1, -1. So it's the only example I want you to know. It's come up in the VCAR exam a couple of times. Last time was probably 3-4 years ago, but it's still something that could likely come up. So good to know H2O2 is the only time you need to know oxygen is something else. Hydrogen, anything other than +1 has not really come up on an exam for about 20 years, so I wouldn't worry about it too much. Hydrogen is always +1. The next and last rule is the sum of all oxidation states must equal the charge in the species. So I've already talked about this in like sodium chloride there. It had to be 0, so +1, -1. So in these cases here, you need to work through them. So I put all 3 cases here because I think they're really good examples, and so you can have a look at sort of where you determine what's going on. So in our first one here, in your carbon dioxide, you'd work off your oxygen first, which is -2, because we know that oxygen is always -2 unless it's hydrogen peroxide. So here your oxygen is -2, you therefore have sort of -4. So therefore, to get 0, you need +4 as your carbon. Again, here you've got oxygen again, -2, you've got 4 of them, so you've got sort of -8. You need to get to -3, so what's the difference between those two? Well, it's +5. And then over here, well, you know what each of these are, so you can sort of work it out that it's going to be +1. There's no real sort of hard work going on there to determine that. It's all pretty sort of straightforward stuff. All right, so continuing on, this is our example from before. So I had 3 different examples here, and I said, which of these is redox? So you should be able to determine pretty quickly which of these is redox. And the best way to do this is to look at, this is always my first inkling, and it's why it's the first rule. Which of these has an oxidation state of a free element? If you look at the 3 of these, there's no free elements here, there's no free elements here, there are 2 free elements here. So given that there are free elements, it's more likely it's going to be redox. It doesn't say there will be, it doesn't mean there will be, but it's more likely. So therefore, I'd look at these and go, all right, there is a change, because these are now in a molecule, and in a molecule, they sort of act like ions. This is +3, this is -1. Therefore, there is a change. The aluminium here has gone from 0 to +3. That means it has lost electrons. It has gone through oxidation. The chlorine gas has become chlorine ions, essentially in a molecule or in a compound. And this chlorine gas was an oxidation state of 0, and now it's an oxidation state of -1. So it has gained 1 electron each, and therefore we call this reduction. So non-oxidant, not redox, not redox, redox. So if the oxidation state reduces, then the species was reduced. So Cl goes from 0 to -1. If the oxidation state was increased, then it would be oxidized. Now, question to everyone who's watching this, and have a think. There's no way of you really to respond to me. What's going on here in terms of the reductant and the oxidant? So take a second, have a think. What do you think? Well, I would sort of think of it like this. The aluminium has essentially been oxidized, therefore it has caused reduction of the Cl2. So therefore this is the reductant. The chlorine has gone through reduction and has caused oxidation of the aluminium. Therefore this is the oxidant. So the chlorine gas is the oxidant, the aluminium solid is the reductant. That's the best way to go about it. So now we understand that. The next sort of basic step is formulating half equations. So you should have sort of been through this in Unit 1, 2, but we're going to go through it again. Sometimes you'll be asked to create half equations. And when you are asked to create a half equation and it's not in your electrochemical series, which will be on your data booklet, which at the time of recording this, you still don't have your new data booklet. So just for the information, just so everyone is on the same page, for this year, and so for this new study design that's covering 2024 to 2027, there should be a new data booklet. It is currently not released at the time of recording this. So utilize the old data booklet where you can. The old data booklet has everything you need. It does not lack any information that the new study design has. There's just irrelevant stuff on it now that will get removed. Essentially, the old data booklet is perfectly fine, has everything you need. Now, if you go to the electrochemical series on that data booklet, it doesn't have everything. And sometimes you need to create half equations that are not on there. And therefore, you need to use a method called COES. Now, this COES method works pretty straightforward. You have your pairing. So you have, let's just say, you're going from dichromate to chromide ions. It's a very common example VCAR likes to use. So that would be like Cr2O7 -2 to Cr3 plus ions. Now, it's a very, very common example. VCAR loves this example. You work with that example and you would, first of all, you'd put those two on the page and draw an arrow and leave a bit of a space after. So you write the dichromate, leave a bit of space, arrow, chromite ions, a little bit of space. Those spaces you need to fill in. Essentially, you'll go through this method. You'll first of all balance your key atoms. Now that would start off with the dichromate. So it would start off with the chromide in there, or the chromium that's in there. So the chromate ions and the dichromate, you'd need to sort of alter their sort of coefficients to ensure that the chromate ions are balanced. Don't worry about the oxygens yet. You then balance the oxygens, but you don't balance the oxygens by changing coefficients. You balance the oxygens by adding H2Os to the side with less oxygens. So you balance that out by adding H2Os. You then balance the hydrogens, which you probably threw out of whack by adding in H2Os, by adding H plus ions to the opposite side, or the side that has less hydrogen. So that's how you balance it out. Now you will have probably thrown the charge out of whack because these have a charge. So then you need to add electrons. Now, if you've been told that you are going to draw a reduction half equation, you should know that reduction involves gain. You should know the electrons need to be on the left. So if you are asked to write a reduction equation or a reduction half equation, and you are given the two starting molecules or compounds, whatever they are, and you put it all on your page, and for some reason your electrons are not on the left side, they actually end up on the right side, you've done something wrong. So that's a good sort of hint to you to go, I've done something wrong. I need to take a step back and redo everything else that I've done. And that's reasonable. And that's why it's important to know that reduction is on, like, your electrons are always on the left, and then in oxidation, your electrons are always on the right. It's good stuff to know so you can sort of fact check yourself as you're going through. So as you can see here, you balance the charges by adding the electrons, and then don't forget the states. So add states last. So add all your states in last and make sure you don't forget them. That's like completeness sake. In an exam, you're not going to get marks if you don't put states. You have to put states down. Really important. So your COES method is really useful. The only issue with your COES method is that we make an assumption that the medium is acidic. Now, I want you to take a think. Why do I assume using this method that the medium is acidic? Well, it's this step here. This step here assumes acidity. Why? Because H plus ions are acidic. They're just naturally very, very acidic. They are essentially what we measure in pH. You will have learned that in Unit 1, 2. But H plus ions are really our measure of pH because they're protons. It's what we work with. Now, because we assume we are acidic, or we are told we are in an acidic environment, we use COES. Now, what happens if in the question it says that the medium is basic? Now, this would only be if the question mentions it. If the question mentions nothing and wants you to form a half equation, you assume acidity. You assume that the medium is acidic, or like, slightly acidic. It doesn't need to be super acidic, but that is an assumption you make. The only time you will use this second method I'm about to go through is if you are told in the question you are in a basic environment, you are in an alkaline environment. That is the only time you will use this. And in this one, you use the exact same method with an extra step. There is one extra step added in. And that extra step is after these hydrogens. So after you've added the hydrogens in and you've added these H pluses, you don't want them. You want to get rid of them, but you've got them there. So how do I get rid of them? Well, the best way to get rid of them is make them into something else. So you add OH ions, the same number of OH ions as there are H pluses, and you add them to both sides. Now, the OH ions on the side with the hydrogens, let's say the hydrogens are on the left side of the equation. You add OH ions to the left side of the equation. There were 4 hydrogens, so you add 4 OH ions. What does that make? It makes 4 H2Os. You combine them and make 4 H2Os. But you only added hydrogens to the left side of the equation because there was water on the right side of the equation that had increased your hydrogens. Well, now you need to cancel. So you do some cancelling. There might be less water on the right than what there is on the left. So now you cancel out the ones on the right and you make your coefficient of your waters on the left a little bit less. So you cancel out your waters accordingly. And then you add your 4 OH ions to the right side as well. Because you added 4 to the left, you must add them to the right. You're not balancing at this point, so you can't just add one or the other. You need to make sure that you cancel out appropriately, and then you make sure that you balance appropriately in terms of if you've added 4 to the left, you must add 4 to the right. That is an important step. You are not balancing out oxygens. You're not balancing out hydrogens. You're not doing that anymore. You're essentially trying to cancel something out. So by trying to cancel something out, you need to add to both sides, left and right. So really important here. This is only a method. This COES with a double H is the only time you would use this method is if you are told it is a basic or alkaline environment, and that is super duper important. Everything else is the same. It's just this extra step of adding OH ions. They will combine with the H pluses to form water, and when they combine with the H pluses to form water, that's what you get. So from here, we need to sort of then talk about, well, what is actually going on in redox? So what's going on in redox is we're transferring electrons, but what we do by transferring electrons is we essentially transfer energy. And what's really important is that when we transfer energy and we do it all in one beaker, we call this a direct reaction. And really, unfortunately, with a direct reaction, they're really easy to do, but they're really useless. You get chemical energy to thermal energy, which is not something that we sort of want. Chemical energy to thermal energy is a bit useless in our eyes. We don't really like chemical energy to thermal energy. Thermal energy is hard to work with, and we don't find it useful in everyday life. However, we can use cells. And the use of cells is essentially that we can get chemical energy and we can convert it into electrical energy. So we can take the chemical energy and we can convert it into electrical energy. So electricity is much easier to store and control, and thus much more useful. And redox is essentially the transfer of electrons. So if we force those electrons through a wire, instead of allowing them to directly react in that sort of direct singular environment, instead of allowing that transfer to happen in a single environment, we can sort of force it to happen through a wire. We can sort of connect things with wires and say, hey, react. But hey, the only way you can do it is if you send your electrons through this wire. By sending the electrons through the wire, we essentially get electrical energy. That's how current forms, that's how voltage forms, and that's how we get electricity. And this process occurs in what we call galvanic cells. And as I said, it produces electricity. Now, I hope you know what galvanic cells are by now. I hope you know how to draw one. If you don't, or if your galvanic cells don't look slightly like what I draw, do what I'm doing. So this is what your galvanic cell drawings should look somewhat like. If they don't look somewhat like this, then you need to start drawing them like this. This is a basic galvanic cell. What's really important about a galvanic cell is that it has 2 electrodes. It has an external circuit. It has 2 solutions. or 2 beakers, and it has a salt bridge. They are the most important steps and the most important things you must have in your galvanic cell. Now, yes, galvanic cells will slightly change depending on what you're putting in there. So if you're putting in like a gaseous electrode or a porous electrode, you're going to have some differences here and there, and that's normal. We're not opposed to that. But it's super important that you understand that the galvanic cell drawing must have these basic things in there, and that's important. Now, what's also really important is that a cell does not make up a full battery. As much as that cell there looks like a battery is the whole bunch of cells. So a singular cell is not going to be strong enough to power pretty much stuff on. You're not going to get anything powered by a singular cell. Lots of cells together are going to power lots of things, and they're going to produce lots of power and enough to, use your phone, use your laptop, electrical vehicle, etc. All those things. So really important that if you want to form a battery, you need multiple cells. You cannot get away with forming a battery from just one cell. It doesn't really work like that unless you're working with maybe like a fuel cell, and they do produce a fair bit of energy, but even then, it's probably not going to be enough. You need multiple cells to form a battery. It's a really important idea to get your head around. So let's look at this example now. So we're going to use a very basic example, and that basic example is zinc and copper. So if you looked at your electrochemical series right now, so I hope you probably all either have a link up with your electrochemical series, or not your electrochemical series, your data booklet, or you've got your data booklet in front of you. If you don't, you need 5 seconds now to get it up. Search up VCAR data booklet, and it should come up. I can literally go across, and I have mine up here. So I've got my data booklet up here, just on another page, which you cannot see. So with my data booklet up, I know that the electrochemical series is on page 4, and given that the electrochemical series is on page 4, I know that zinc and copper will react. I know that zinc solid is, if I go to my book, I can see that zinc solid sits at about, where am I? I think I've lost it. I had it in my eye before. There we go. Zinc solid sits on the right side of the equation, and it's at negative 0.76. Copper 2 plus is on the left side of the equation, it's at plus 0.34. So I know these are going to spontaneously react, and that is the reason why, in this case here, I've got zinc on the left, I've got zinc solid and copper 2 plus as my reactants. I understand that the zinc, from looking at my electrochemical series, I understand that zinc is going to go through oxidation because it's going to lose electrons. It's going to go to 2 plus. I know that copper is going to gain electrons and therefore go through reduction. Therefore, I can say, zinc occurs at the anode, because the anode is the site of oxidation. Vow to vow, A to O, vow to vow, anode to oxidation. That is the best way to remember it. It is negative. In our spontaneous redox, it is negative, and that's super important to understand as well. We then therefore know that there's zinc 2 plus in that solution, aqueous. On the other side, we have the cathode. Now the cathode is positive, so the cathode is the happy cat. It's positive, so given that the cathode is positive and we have a copper solid electrode that is positive, that's what's going to happen there. We know that copper is in the solution. We also understand that the electron flow is always anode to cathode. I hope you know that by now, but it is always, always, always anode to cathode. And the salt bridge is made up of KNO3. Now, you might have been told something else, that's okay, but KNO3 is always the one that I use. Really important, the cations, so the K plus goes towards the cathode, the anions, the NO3 minus goes towards the anode. The anode will slowly form more Zn2 plus, and the Zn will be used up as the electrons flow to the cathode, and you get more copper solid formed. And that is a very basic galvanic cell. That is essentially the most basic galvanic cell you can work with. So as you can see here, this is your electrochemical series. Your electrochemical series can show you your strongest oxidant, your weakest oxidant, and increasing oxidant strength. It can also show you your weakest reductant, your strongest reductant, and increasing reductant strength. So from now,